started? All right. So, today we're going to continue looking at rotational motion. We're looking at a new concept known as torque. Now again, in this class I try to teach things from the perspective of what you've seen before, and for that reason, torque is not technically, shouldn't be a new concept, although you might not know what it's called or how you use it on a daily basis. But the notion of torque is one that you are at least subconsciously familiar with. Torque is something that you utilize every day because, as it turns out, most human tools and several human simple machines all utilize torque to some extent. And when I say torque, the phenomenon that I am referring to, and I mentioned this at the end of last class, is, as an example of where torque shows up in daily life, doors. I'm actually not going to use the normal door over there because that doesn't really show up on camera. Instead, I'll be using meter sticks instead of doors. Consider this to just be a really narrow door. The hinge is all the way over here. So this right here where my hand is the hinge of this door. If you want to open this door, what would you think to do to it? Pull it where? On the, wow, I forgot the English language for a second there. On the doorknob. If this is the hinge where my right hand is, where is the doorknob most likely placed? The other side. The other side is all the way opposite the door hinge. Even if you don't necessarily reach for the knob itself, you usually put your hand somewhere on the side opposite the hinge, correct? Have you ever tried opening or closing a door by applying a force close to the hinge? Is it easier or more difficult to do so? It is more difficult. And just, I guess I will show on the actual door real quick. Grabbing the far side of the door is pretty straightforward, but if I instead start pressing right here, not a whole lot happens. And in fact, my fingers are starting to hurt, so test that out if you wish. This phenomenon, the fact that the same amount of force from you can generate different amounts of rotation, is torque. Torque is what happens when you exert a force some distance away from a fulcrum, from a pivot point. And that's what a hinge on a door is. It's a pivot point, a point that the rest of the door is able to rotate about. And whenever you exert force some distance away from the pivot point, so the image up there is meant to be door hinge, length of the door, I'm applying force here, and the door starts spinning in this direction. Torque is what happens, torque is what is generated when you exert that force some distance away from the hinge. Torque is what happens when you exert a force at a radius from an axis of rotation. Those two things combine together, multiply together rather, in order to generate a certain amount of torque. And torque can be thought of as the angular counterpart to force. So at the beginning of our rotation chapter, we started talking about the differences and commonalities between torque and linear motion. We compared linear displacement to angular displacement. We compared linear velocity to angular velocity. I've kind of been describing them as counterparts between these two worlds. They measure the same basic thing, but one is in terms of meters forward and the other is in terms of radians spun, or degrees spun, or full rotation spun. Torque is the angular counterpart to linear force. As we've described linear forces up till this point, their purpose has been to make things start moving in straight lines. Force causes linear acceleration. We know this from Newton's second law. Net force equals mass times acceleration. If you exert force on something, it starts accelerating linearly. Linear force causes linear acceleration. But it is possible to use force to make something spin. You do that every time you open a door, anytime you try to rotate a wheel. Linear force can generate rotational motion. Linear force can cause angular acceleration if you specifically use that linear force to generate torque. This right here is going to be the symbol for torque. This is technically a lowercase Greek tau. It's not technically a T. We use T for other things. You generate torque when you exert linear force some distance away from an axis of rotation. And that torque then determines how much the object is going to start spinning. The more torque you generate, the more spin that force is able to create. And you can increase the amount of torque that you generate by either increasing the force you are using, but also by increasing the radius that that force is applied from the axis of rotation. And to refer back to the door again, that's why the door opens more easily if you exert your force over there rather than here. This point has a very small radius away from the door hinge, whereas that point has a much greater radius away from the door hinge. A much greater radius generates more torque. More torque means more spin, even if you're using the same amount of force. Sound all right so far? Sound familiar, I hope, at least? All right. This concept shows up way more often than you might think it does. It happens every time you open a door with a hinge, be it a building door or a car door, because they rotate similarly. It happens every time you drive a vehicle, because as it turns out, wheels rely on this too. In order for this wheel to start spinning, torque is required. And this is sometimes why car commercials will talk about the torque that their engines are able to generate. To apply torque to a wheel like this, I have to apply a force some distance away from its axle of rotation. And if I grab the wheel here and apply a force in this direction, I specifically applied it a distance away from the axle at radius r. If I instead apply force directly to the axle at a radius of 0, I don't actually cause any rotation. I just cause linear motion. It's only when the force is applied some distance away, some radius away, that rotation is caused. So, if I am acting just on the axle, my linear force creates linear acceleration like it always has. But if the force is applied some distance away from the axle, you generate torque, and torque causes rotation to start. Torque causes angular acceleration, whereas linear force causes linear acceleration. You don't even have to be holding the wheel in order for this to work, because a wheel rolling along the ground does the same basic thing. In order for this wheel to start rolling forwards, there's some frictional force pointing backwards acting on the edge of the tire, which is again some distance away from the axle, which is why it doesn't spin if I'm just moving it around by the axle. It requires the friction from the road to actually get rotating. So torque exists in every door, in every wheel, and really about every tool that humans designed to use with your hands. Lost my train of thought there, sorry. What are some of the first tools you think humans ever invented? Hammer? All right. Purpose of a hammer is you got usually a heavy thing at the end of a stick, and then you use the length of the stick to swing that heavy thing at something else. The stick is a lever arm with a radius R, and so by putting the heavy thing at the end of the stick rather than just holding it in your bare hand, you are generating torque and using the stick to kind of multiply your force output. Whereas instead, you could just rip the head off the hammer and slam it down with your bare hand, but that's not quite as effective, is it? I wouldn't recommend trying to punch nails into boards. I probably tried at one point, it wasn't fun. Hammers use torque. Pretty much anything with a handle uses torque. That is not only hammers, it includes swords, axes, screwdrivers, wrenches, and most sporting equipment, because baseball bats, golf clubs, tennis rackets, cricket bats, anything that you swing at something else is radius R that you are applying force at rather than with your bare hands. So most machines are an application of torque, and most sports, except maybe football, are applications of torque. So again, it's literally everywhere. Sound all right so far? All right. So, this is the formula for torque. This tau on the front is the torque itself. Torque is equal to radius times force. There is this little perpendicular symbol here that I want to acknowledge. In order to correctly generate torque, the force and the radius have to be perpendicular to one another. If you want to make a door spin, you usually push into its surface, correct? That would make that force perpendicular at a right angle to the length of the door's surface. This is a requirement to generate torque correctly. I would not be using the door properly if instead of exerting a force perpendicularly to its length, I was exerting a force parallel to its length, trying to push it in or out. That does not quite generate torque. That just makes me look kind of silly. So that force is parallel, that doesn't make anything spin. The force has to be perpendicular to the radius. So that's a small requirement to generate torque correctly, and that's why that symbol is in the formula. But torque equals radius times force. The tau here is the torque. Torque is technically a vector, but angular vectors really only point clockwise or counterclockwise. Those are the directions that an angular vector can have. But it is still technically a vector. It points somewhere. And it is measured in units of Newton meters, which is not actually newtons over meters, it's newtons times meters. And that's because the formula for it literally has you multiply newtons times meters. So that's all the unit is. Questions so far? All right. Let us practice that formula very briefly. Wrenches are tools that utilize torque to make something spin, because if you want to screw in a bolt, you have to get it rotated. In this case, we are going to apply a 12 Newton force right here at the end of our 1 meter long wrench. So the wrench is 1 meter from the rotating part to the end of the handle. We're applying 12 newtons directly to the end of the handle. How much torque do we generate in such a scenario? applied? 12. Our radius is 1. Our applied force is 12 newtons, and so we get 12 newton meters, again, is our unit. Now, just for, sorry, was that a question or was someone just clearing their throat? Apologies, my ears are playing tricks on me. Now, what happens if we cut the length, sorry, got the order wrong. What happens if we double the length of the handle? If we just use a longer wrench? If the wrench was longer, our radius would be twice as big, so we plug in 2 meters instead of 1. Double the length of the handle, and you get double the torque without even having to exert any more effort. Same amount of force, but if your wrench is twice as long, you generate twice as much torque, and getting that bolt to start spinning should be about twice as easy. Conversely, if we cut the length of the handle in half, so instead of a 1 or 2, we plug in 0.5, the same force generates half as much torque. So in general, if you're having a hard time getting a screw or a bolt to start rotating, acquire a longer wrench or screwdriver. There's an old quote, which I believe is attributed to Einstein, saying that if you have a lever arm long enough, you could move the earth, which is technically true. You know, the amount of force I can output would be enough to move the planet if I had a wrench, you know, the length of the solar system with which to do so. It's not practical, but it's theoretically possible. Questions so far? All right. Now, this again does apply to a surprising amount of aspects of human life and human engineering. Again, most tools utilize torque to some extent, and again, that does include sports equipment. What I'm about to do is I'm going to take this meter stick, I'm going to hang this clip from it, I'm going to put it right here at about the 10 centimeter mark, and I am going to hang, whoops, how much is this? 1 kilogram, dagnabbit. I'm going to hang 1 kilogram from the end of this clip. Now, if I hold the meter stick here, this 1 kilogram weight only has a radius of about 10 centimeters from the axis of rotation that is my hand. And so this is not generating that much torque. It's still kind of uncomfortable to be holding it like this, but it's doable. And in fact, I would like to ask if any student would like to volunteer to hold this in their hand to see about how much torque this generates. See what it feels like to be generating this, to be counteracting this much torque. I'm not going to force anybody. It's okay if no one wants to volunteer. You can do so. Oh, hello. Hi. Would you like to volunteer for something?
If you need me to.
Welcome back, first of all. It's always good to see you.
What do you want to do?
Hold this.
Just hold it.
Yep.
Okay.
Now, about how much effort are you exerting right now?
Not a lot.
Not a lot. All right. So, This object is currently in rotational equilibrium. Basically like how when net force is equal to 0, things don't accelerate. When net torque is equal to 0, things don't accelerate. So right now, this weight is generating a certain amount of torque to try to make this thing spin, and Will is generating enough to hold it up and keep it from spinning. Now, if I increase, yes, if I increase the radius, let's just go halfway.
Thank you.
If I increase the radius, the distance that this thing is from Will's hands, that should increase the amount of torque that this weight is creating. Would you agree that you are now working harder to hold this thing up?
Absolutely.
Absolutely. He needs 2 whole hands now. In order to keep this thing in rotational equilibrium, more counterclockwise torque is needed from Will in order to counteract the clockwise torque being generated by this thing. And furthermore, if I would make it go even further down, that increases the radius even more. That's even more torque needed to counteract it. Thank you very much. Welcome back. Always good to see you.
I'll see you later.
You are welcome to try to see it. What am I trying to say? If anyone would like to feel about how much torque that is generating, how much effort that takes, you are welcome to try. But even if you don't want to today, lab in about 2 weeks will cover this principle and you can test it out there as well. Just as linear force generates linear acceleration, but only when imbalanced, the same is true for torque. Only imbalance of torque creates net acceleration. Only an imbalance of torque causes things to start spinning. So if net force equals 0, you get an acceleration of 0, linear acceleration of 0. And if net torque equals 0, you get an angular acceleration of 0. Basically, if all of the torques acting on something are balanced, the object won't rotate. It will remain in place, or it will remain in equilibrium, meaning it might rotate at the same speed, or it won't be rotating at all. We call this, again, rotational equilibrium. It's still a type of equilibrium, and it's still the same basic concept. Either net force equals 0 or net torque equals 0. And basically, anytime something is not currently spinning, the net torque on it is 0, like how if something is not currently moving, the linear net force on it must also be 0. But examples of places where you want rotational equilibrium are seesaws, like this, or balance beams, or teeter-totters, or whatever you want to call them. This object, as it is currently pictured, is in rotational equilibrium. There are currently forces acting on it. There are currently torques acting on it. But as long as they balance out, it doesn't spin anywhere. Does that make sense? Again, similar to how there are currently forces acting on all of the stuff on my desk, but as long as they cancel out, they don't move anywhere. But in this case, as long as the torques cancel out, no rotation takes place. So if you want to make something spin, you need to generate enough torque to get it moving, and you can generate more torque by either using more force or using a longer lever arm. If you don't want something to spin, you have to make sure that all of the torques currently acting on that item add up to 0. Now, to practice this, I'm going to put some numbers to this seesaw teeter-totter example. When I was a kid, playing on the playground with my siblings and my cousins, we would usually play a game of going to the seesaw and trying to keep it level, basically. You know, each kid would sit in a certain spot or stand on it in a certain spot to try to keep the platform as level as possible. Were we the only ones that played that game? Or does that sound familiar? Okay, cool. Glad to know I'm not alone. These two kids are trying to do the same basic thing. Except, you know, these kids are different sizes, as all humans tend to be. The first kid has a mass of 60 kilograms and is currently sitting 1 meter away from the fulcrum. The second kid has a mass of 30 kilograms and is currently sitting, well, we don't know what distance away. This kid needs to position themselves in such a way that the platform doesn't spin, that rotation does not take place. Before we start doing the math to prove this, how far away do you think this kid needs to be sitting to balance this out? 2 meters. Very good. They have half the mass, they weigh half as much. They should have to sit twice as far away to generate the same amount of torque. So your instincts are on point there, and I'm hoping this feels like concepts that you've at least noticed before. And now we'll prove that with numbers. To do this, I'm going to show how you can calculate or prove situations where net torque equals 0. If you want the net torque to be 0, you need to figure out all of the things acting on an object that are currently generating torque and add them all together, factoring in whether they point clockwise or counterclockwise. Because those are the two directions that torques can point. Really, those are the directions that any rotational vector can point. Just to kind of review, I'm going to be using my hand as a lever arm on the meter stick right now. If I stop holding the meter stick up, it's going to do this. Is that clockwise or counterclockwise? Yeah, from your perspective, from your eyes, this is a clockwise motion, and that is being caused by a clockwise pointing torque. Since my hand is currently the fulcrum, and the weight of the meter stick is concentrated on its center of mass, we will cover that in definite terms this week as well. The weight of the meter stick is here. I'll show that further by just hanging this thing from it. The weight of the stick and the mass is here, and so that force pointing in this direction on this side of the fulcrum is going to try to make it spin in this direction, which again from your perspective is clockwise. If I turn that around, like the other side of the seesaw, this would now be counterclockwise. Wait. Yes, sorry. I was looking at it from my angle by accident. So, the same direction of force, the weight still points down, on the opposite side of the fulcrum generates an opposite direction torque. So when looking at seesaws and rotating torque questions, it's important to think about, and sometimes you can even just take your hand to check, radius this way, force this way, what direction should it be spinning in, factoring those things in. In the case of wanting to maintain a rotational equilibrium, you need to make sure that all the torques add up to 0. That's one way to think about it. But another way to think about it is to check that all of the clockwise pointing torques are canceled out by all of the counterclockwise pointing torques. You could kind of work it either way. You could consider clockwise to be positive, counterclockwise to be negative, in which case they would add up to 0 as we normally think of forces. But I have some students prefer to think about it as, rather than adding all of them up on one side, kind of setting one side of the balance beam against the other, all of the counterclockwise opposed by all of the clockwise. You could think of it either way. I'm going to try to demonstrate both thought processes in a second. But the main point is, if you want something not to spin, the torques have to be in equilibrium, the torques all have to cancel out, factoring in clockwise versus counterclockwise. And I'm going to show how to then use math to prove you guys right that this kid has to sit twice as far away. questions before math? All right. So we have our balance beam here. We've got two kids. And I want to make it absolutely clear that the forces that are currently going to be generating torques are the weights of each of these two children. They each weigh a certain amount, and their own forces of gravity are pressing down on either side. So to figure out the force on either side, we need to double check the weight of these two people. We know their masses though, so that's pretty straightforward. So mass 1 is 30 kilograms. Therefore, the weight of that particular human is going to be their mass of 30 kilograms times negative 10 for gravity. And so their weight is negative 300 newtons down. Kid 2 has a mass of 60 kilograms. So their weight is going to be 60 times negative 10, negative 600 newtons down. So it is very specifically the forces of gravity acting on each of them that is causing the torque. Mass by itself doesn't cause torque, it's the force that's generating torque. I just wanted to address that first. So these are the forces acting on either side. Note that the forces are not the same size, but we can still create a balanced rotational equilibrium by making sure that these two forces generate equal and opposite amounts of torque. Radius 1 is unknown. I just decided that the kid on the left is 1 and the kid on the right is 2. But we do know radius 2 is 1 meter. So, how do we prove this mathematically if you wanted to show me your work? Again, there's two ways you can think of it. There's the net torque equals 0 approach, in which case you have to factor in that the two torques here are going to point in opposite directions because the two kids are sitting on opposite sides of the fulcrum. Kid number 1, force down on this side of the fulcrum, that is going to make it start spinning counterclockwise. Meanwhile, kid 2, on the opposite side, downward force, but on the opposite end, that is going to try to make the whole thing spin clockwise. So even though the forces point in the same direction, the torques don't. If determining the direction of torque takes practice, that is okay. Again, all the rotation stuff is weird. It's allowed to take a minute. But their two torques point in opposite directions. We have to factor that into our work. Torque 1 plus torque 2 must equal 0 for this object to remain in place. Kid 1's torque is trying to make the whole apparatus spin counterclockwise. So that's a force of negative 300 newtons times some unknown radius. Kid 2's torque is going to be equal to kid 2's weight times kid 2's radius. So kid 2 weighs twice as much and is sitting at 1 meter. And these two things need to add up to 0. Are you guys okay with jumping from torque to the formula for torque? I realize I kind of skipped a line there. You know what, I'll backtrack. Apologies. Torque 1, formula for torque is radius times force. So torque 1, I'm going to write in radius 1 times force 1. And for torque 2, I'm going to write in radius 2 times force 2. equal to 0. Does that make sense? All right, I'll plug in the numbers again. So I wrote it a little bit backwards, but that's okay. R1 is unknown, but we do know, again, the weight, the force of gravity acting on kid 1. As for kid 2, we know both their radius and their weight. And these two torques have to add up to 0. Conceptually, as for where everything went here, where it's going, feel all right? Okay. Now our goal is to get R1 by itself, so I'm going to try to simplify this a little bit. Negative 300 times R1 minus 600, just negative 600 times 1 is going to be negative 600 equals 0. Negative 300 times R1 equals positive 600 if we add 600 on both sides to move it over. Then to get R1 by itself, what should we do to both sides? Divide by what? Negative 300. So for the next step, I'll write out R1 equals positive 600 over negative 300. And that will give us a final answer of negative 2 meters. The 2 meters is correct. You guys did say that kid 1 would have to sit twice as far away in order to generate the same amount of torque. The negative implies opposite side of the seesaw. If we write in positive 1 for kid 1's radius, the negative 2 over here means that kid 2 is sitting in the opposite direction. So that's why that's there. That's what it means. It makes sense, and it's a good thing to have on our answer. Sound all right? All right. So, as for how to use math to derive this answer, feel all right? All right. There is a different way you could think about it. I have some students who prefer to think about it this way, so I just want to address it before moving on. I have some students who prefer to separate the two forces between clockwise and counterclockwise, kind of showing that the two directions need to be balanced in order for you to not be spinning. So it's the same basic procedure, just instead of them being on the same side canceling out, they are equal on opposite sides of the equal sign. And you get the same answer, it's just a different way of thinking about it. Kid 1, their torque is trying to make it spin clockwise. Kid 2, their torque is trying to make it spin counterclockwise. So unknown R1 times negative 300 equals known R2 times negative 600. And the same basic process would still give you 2 meters. The answer does come out positive though. Setting it up this way just kind of assumes you know what is acting on what side. It's just a preference for some people, and you can do it that way if you want. I kind of prefer this method because it helps keep all my positives and negatives straight, but how you think about it is valid. There are multiple ways to get to the right answer. How do you guys feel? All right. Any questions for right now before we head towards the end of today's lecture? All right. Now we're about at the end here, so I'm just kind of using this to lead into what we're talking about on Friday. Does this make sense? Some people are nodding. That's good to see. Does this not make sense to anybody? It's okay if it doesn't. What would you describe as the main differences between how this seesaw is constructed versus how this one is constructed? The thingy, I'd call it a fulcrum, but thingy is not inaccurate. The fulcrum is placed under the middle of the seesaw in this particular case, whereas in this one it isn't. It's placed all the way off to one side. Now, if we assume that this is a solid uniform piece of wood in both examples, say it's the same seesaw in both, someone just moves the fulcrum for some reason. Take this thing off. Would you expect this seesaw to balance out by itself without anyone sitting on it? No. Very good. So first, I will show an empty seesaw with the fulcrum placed under the middle of it. It's hard to do totally perfectly, but I've placed my finger acting as the fulcrum right on the midpoint of this object. I'll even rotate it to show. This is a 2 meter long meter stick, so I'm putting my finger right there under 1 meter, 100 centimeters. And it's not totally perfect for a human to do unassisted, but I can level it right there on that spot. This picture, on the other hand, looks more like this, in which case this happens. Now, that piece of wood with this object there by itself is not rotational equilibrium. However, you can do what this kid is doing. Place a weight on one side of your jank unequal fulcrum and actually get this thing eventually to balance. It's not rotating, so this is rotational equilibrium. My question is, this mass is currently generating torque. We've got its weight some radius away from my hands acting as the fulcrum. What's on the other side generating the torque to balance it out, though?
The weight of the stick.
The weight of the stick. Very good. On a well-constructed seesaw, the fulcrum being placed in the middle is not an accident. The fulcrum here is placed under a point known as the center of mass, sometimes called the center of gravity. Those are synonyms. And when the fulcrum is under the center of gravity, the mass of the object doesn't end up generating any torque. And that's because its weight is at a radius of 0 from the fulcrum. Doesn't matter how much something weighs, if you are balancing it right underneath its center of mass, it doesn't fall, because there's no torque being generated if the radius from the fulcrum is 0. It could weigh 8 million tons, but if radius is 0, there's no torque, and it will not spin off of that point. Technically, you can do this to support any object. As long as its center of mass is supported, it won't fall. Like with my water bottle, if I support its center of mass, it doesn't fall. If I don't support its center of mass, it falls. So in this case, since the fulcrum is not under the center of mass, the weight of the meter stick actually starts mattering. The weight of the stick can actually generate torque in this context, and you have to have a child here balancing it out, or in this case, a piece of metal. So, one takeaway from this is that the center of mass of an object can generate torque if the fulcrum is not directly underneath it. And two, an object's center of mass does matter for rotational purposes. Objects like rotating around their center of mass. And so on Friday, we will discuss center of mass and how it affects moment of inertia and angular momentum to wrap up our rotational week. Sound good for right now? All right, that was a lot of information. Let me know if you have any questions.
Have a wonderful day.